So we are very happy to have Heather Lee from Purdue University. So she will talk about homological mirror symmetry for open Riemann surfaces from pair of Pans decomposition.
Thanks for the invitation and for coming to my talk. So we want to talk about puncture surfaces. And we want to do mirror symmetry, so let's consider a surface. I'll denote that by A, near the tropical limit. So that means we want to think of C as belong to a degenerating family of hypersurfaces in C star 2, and define each of them is defined by a Laurent polynomial. And so here, this alpha is a finite sum. So alpha belongs to a finite set of integer lattice, and this mu here is a convex piecewise linear function defined on A. So this is Minkowski's story for pair of Pans decomposition. Let's not dwell on this too much, but the point is that so we have this Riemann surface that are hypersurface in C star 2, and we can take the log of it that maps to R2, and as t goes to infinity, in the tropical limit, it degenerates to a graph like this. And the complement of this graph has several different components. We have one component corresponding to each monomial in this defining equation of the hypersurface. So each component, you can label it by one of the alphas in this set. And once we do this, there is a pair of Pans decomposition corresponding to each vertex, and I'm labeling each vertex as P alpha beta gamma. So feel free to interrupt me with questions, but the point here is that we have this hypersurface near tropical limit, and we do this log and take the limit, and it degenerates to this graph with a number of components equal to however many monomials we have here. Okay, and so ignore the top for a second. If you look at this example of a pair of Pans, you can write it in this way with 3 different monomials. And then in this function, so this graph is a singular locus of this Legendre transform function. So this is a maximum of a bunch of functions, linear functions. So there are 3 monomials corresponding to 3 linear functions, and if we do the maximum, this graph is a singular locus of the Legendre transform function. So here, and like right here, this line C1 equals to C2 is where C1 and C2 are about the same size. So. Anyway, so to talk about mirror symmetry for this puncture Riemann surface, well, this mirror is familiar to a lot of you. It's been talked about in this conference a lot, but I think it traces back to Horvath. But anyway, so this Abzeda, Aru, Kazakov studied SYZ mirror symmetry for this. Well, I won't talk about that much because it's their work. But the mirror of a hypersurface like this is a Landau-Ginzburg model where Y is a toric variety, a toric manifold of complex dimension 3, and is described by the moment polytope in this way, where once we degenerate to this graph, we can think about introducing a third coordinate that comes out of the board. And then this polytope sits above this function. So in this here, the function here is 0, and then this function C1, C2 sits above it. So here, this polytope looks like a tilted corner of a wall. So the mirror of pair of pants is a C3. And then the superpotential on it is going to be a holomorphic function from Y to C, and is going to vanish to order 1 on each of the irreducible toric divisors. So it vanished to order 1 for each of the facets. The irreducible toric divisor corresponds to each facet. Okay, so and it may be quite strange that we have a dimension 1 curve, and then the mirror is like 3 dimensions, but this is because we don't have a good torus vibration on this singular thing. So if you look at the dimension of the critical locus of this W, then it's actually dimension 1. So the dimension 3 is to you replace this this one by something with a bigger dimension in order to have a toric vibration to do XYZ. So anyway, so and then so the superpotential for pair of pants, the mirror of the pair of pants is XYZ, where XYZ are coordinates on the C series. Okay, so let's go, and we want to talk about homological mirror symmetry. So this is the direction of homological mirror symmetry we want to study. We want to study A model on the Riemann surface, and then B model on the Landau-Ginzburg mirror. So it's a derived equivalence with the A model. We want to use, instead of using the Foucault category, we want to use Rav Foucault category instead, because C is non-compact. And so whenever we have non-compact manifold, we want to use Rav Foucault category. And the B model, we want to consider category of singularities. We'll talk about these things later. So there were some related work for this. This opposite Aru, Efimov, Kazakov, Orlov paper. They studied puncture spheres and multiple covers of it. That covers a lot of Riemann surface already, and there's this work by Bachland and some others. But we want to do it in a way that we decompose the Riemann surface into pair of pants and put it together. So it's a little different perspective. And you'll see that opposite thesis also, there are ingredients of that in this. This also have influenced by that. So that's the direction of homological mirror symmetry we want to study. Aru and opposite also are studying the case where that direction with the A model on the Landau-Ginzburg mirror. Okay. So we focus on this direction. So about Rav Foucault category, let's first talk about the objects that we want to consider. So Rav Foucault category contains both compact Lagrangians, like this red curve here, and it also contains non-compact Lagrangians. And so any puncture Riemann surface, we can think of it as a Liouville manifold, where we just model each puncture by the symplectization of this S1 here. So it's a cylindrical end. And we want to only consider Lagrangians that are conical, so it's parallel to the Liouville flow in this cylindrical end. So we have compact Lagrangians and also non-compact Lagrangians that are parallel to the Liouville flow in the cylindrical ends. And in order to be easier to study, let's find a split generating set of Lagrangians to consider instead of thinking about all of them. So the split generating set we are considering is this very big set. So, but actually, if you just want to think, it makes talking about mirror symmetry easier to have this many Lagrangians, but you don't need this many. You can just have, so let's first talk about what are this. So for each component alpha, we are going to have a set of Lagrangians L alpha k. And each L alpha k is going to contour this component. So see this green curve L alpha is contouring the C alpha, and this red curve L gamma is contouring this middle component C gamma, and then this blue one is contouring C beta, and then it's going to twist approximately k times, like proportion orthogonal to k times m. I'll explain that a little later. So, well, it's going to be parallel to the Liouville flow in the cylindrical ends, but for each bounded edge, L alpha k will twist this number of times. So what is this n? So let's restrict to this edge. I call it, this is edge L gamma. So on this edge L gamma, n is the length, the integer length of this edge, and then k is the number that I'm twisting for this Lagrangian, and then plus this delta thing. If you only want to think about category alone, you don't need this delta. I just put it there for the mirror symmetry to work better. So this delta, so you get the delta alpha gamma and then delta gamma alpha. You can choose them so long as their difference is equal to 1 plus the degree of the normal bundle in between these two divisors. So in this example, so the difference between alpha gamma and gamma alpha and so on for gamma beta and delta beta gamma, or like the difference is 2 is the corresponding to the degree of the normal bundle between the two components. So it's just a little adjustment. That's not so important to study the rough category, but it's good for mirror symmetry to work. So those are the L alpha K's. So you can see that here L alpha 2 is twisting twice in this bounded edge. And the red curve is actually twisting -1 times in each edge along the boundary of the middle component, but I added plus 2. So anyways, so those are the L alpha K's, and actually if you just want to compute the rough category, you don't need this many. You can just take L alpha 0 and L alpha 1 for each component alpha. Okay, so any questions? All right. So now about category of singularities. We won't talk about this too much, but I just want to list the objects. So here we have all these objects, L alpha K's, and when we study mirror symmetry, they are going to correspond to this kind of objects, O d alpha k, where d alpha is a irreducible toric divisor. And well, these are equivalent categories. You can pick whichever you like to do computations. And just a quick example that for mirror of pair of pens, we have the mirror C3 with XYZ, and if we have those rings, we can consider category of singularities as like this is an object in the category of singularities for the C3 XYZ, and then we can consider we can replace this by a two-periodic resolution by free resolution, or we can just consider this ring, and then we can think of it as an object, as a matrix factorization of R hat to R hat, and then X times YZ is equal to the superpotential, and so on. So you have these objects, and then you can compute morphisms. Let's not talk too much, but any questions? So, all right. So let's focus on the rough category, and I want to start by this very simple example. Maybe some of you are familiar with, but let's set some notations. So it's defined in the work of Abzey-Sado. So a lot of this is influenced by this paper. So for a cylinder, R cross X1, in order to define a rough category, we need to make a choice of a Hamiltonian. So the choice of Hamiltonian we make is one that is linear near the infinity of the cylindrical end. So it's linear, and then we just define Hn to be n times h. In all of our cases, you can be a little bit more creative about this. You just have to increase. And then the floor, and then once we have this choice of Hamiltonian, we can talk about floor complexes perturbed by this Hamiltonian Hn. So this floor complex will consist of one interior intersection point in the compact part, which is this one labeled by 1 here. But then it's also going to consist of trajectories of the Hamiltonian from the Hamiltonian action. That but there corresponds to rib pores. But if you just but this trajectories is the same as the intersection points. If I flow L1 by the if I consider the time 1 flow of L1 by Hn and then intersect with L2. So instead of thinking about rib pores, it's easier a little bit when you draw to think about intersections. So we'll just say that we have this floor complex perturbed by Hn, and it's generated by the intersection points of the time 1 flow of L1 intersecting L2. Okay, so in this picture, we have just this Lagrangian, both L1 and L2 are L, and then we have this L intersects L twice perturbed by H2, so it's, we wrap it twice. So for each cylindrical end, we added 2 more intersection points. So also, and then we just label them. So far, they're just purely labels. Later, we'll see they actually have an algebraic structure we can put on them. So once we have this perturbed floor complex, we can define the morphism complex for the wrapped Foucault category. So the wrapped floor complex, in this special case where all the higher order continuation maps are trivial, it's just equal to the direct limit of all of these four complexes with the perturbation Hn. And in all of my cases, all the continuation maps are actually just going to be inclusions. You can think of if I perturb by Hn, I'm just going to add more and more intersection points, and the earlier intersection points are included in the later ones. So it's very trivial continuation map in this case. Okay, so yeah, continuation is going from Hn to a bigger Hn, to H of a bigger n. Okay, so in the limit, you get infinitely many generators for the morphism complex of the wrapped Foucault category. So you get all of the powers of X. Well, so far they're not really powers of X, they're just how I'm labeling them. But then we can talk about A infinity products, or yeah, so this is just the second order product, but there are also higher products, not in the cylinder case, but in other cases, by counting triangles bounded by the phi of H2 or phi H1 to the time 2 of L, and then phi of H1, L, and then also L's. You can think about counting those triangles will give us product structures. And then continuation map will induce a product structure on the wrap floor complexes. Okay, so here in this picture, 1 times x1 equals to x1. So you can keep going, and they're just monomials multiplied together. So this gives a mirror symmetry statement that the wrap Foucault category that we just computed is kind of equivalent to this the category of coherent sheaves for C star. This is generated by L, and the other one is generated by O, and they have the same endomorphism algebra. Okay. Any questions? Okay, so I'm going really fast. Okay, so this is the theorem. So now we want to think about how to compute the wrap Foucault category of the big Riemann surface from the wrap Foucault category of each of the pair of pans. So, well, one thing you can think about is just do this for the Lagrangians that we take here, and then just compute by brute force, counting all the triangles and the polygons and so on. And you can do that. You can still compute the triangles, but then the higher polygons are hard to keep track of. And then it becomes necessary that to actually to be able to find a way to decompose, so you can actually get the wrap Foucault category for the big Riemann surface from the pieces. And the pieces comes from the puncture sphere paper that I mentioned earlier. That's a big page, so let's do it bits by bits. So this is fine. We just consider those objects and just work with those objects. And we need to pick a suitable model to compute this rough category. That means we need to pick this Hamiltonian that we use to define the rough category. And well, to begin with, it has to satisfy the property that I mentioned earlier, that it has to be linear at the infinity of each of the cylindrical ends. But in the bounded region, you can be more creative. Yeah, so you have to be careful picking this Hamiltonian, otherwise you can have holomorphic disks that go through the entire Riemann surface, and then it wouldn't, they can't just all come from the pair of pans. So how are we going to do that? So let's come back to this page later, but so there are these restriction maps that we can do. So to explain this statement here, so what are the morphism complexes between two objects on the whole thing? They're generated by, you take the generators of the morphism complexes between any two Lagrangians in the whole thing that comes from the alpha and beta components. Suppose we have an edge. So suppose the alpha and beta components are adjacent. So we have an edge with alpha and beta going through. And then the generators for the global one is going to be, you take the generators for each individual pair of pans. And then in the middle cylinder here, where the pair of pans overlap, you identify by some restriction map. So this restriction map is really in the spirit of Viterbo restriction. And also, Viterbo restriction is for symplectic homology, and Abuzade and Sado did that for OpenString, had an OpenString analog of this. So if you remember, so like Viterbo restriction, for Viterbo restriction, we have like a symplectic like a Liouville subdomain inside the big Liouville domain. So we have like Liouville subdomain inside a big Liouville domain, and there are some parts where you can see here we have some radial coordinates. So if we have so in this case, here is what I would take as a Liouville subdomain, this cylinder here, and the rest would be the Liouville domain. But before we get to that, let's just talk about Viterbo restriction for a second. So the point of the Viterbo restriction is that we want to have a map from the big Liouville domain to the small subdomain. And how are we going to do that? So in the case of Viterbo restriction with the symplectic homology, we have rep orbits. So we have rep orbits from the big Liouville domain, and then we have rep orbits from the subdomain. And so we want to separate them in action. So to do that, they have a Hamiltonian that looks like this. So it's kind of the identity in the subdomain, and then it's kind of, you just have to construct like a Hamiltonian that separates. So you make the action. So if I have a Hamiltonian like this, the action is just the y-intercept of the slope for each. So you want to make the action for the small in action of the rep orbits in the small domain very, very small, and the action of the rest very, very big, so that you can separate them, and then you get the morphism complex of this Liouville subdomain as a quotient complex from the rest by a restriction map. So this is kind of the same idea. We have, well, we can't just have each of pair of pans as we can't simultaneously make all the pair of pans be Liouville subdomains all at once. So we have to take this, construct a global Hamiltonian where for each piece it kind of looks So, and then we will have restriction maps from the morphism complex on the pair of pans. It goes up all the way to here. So this pair of pans, and then restrict to the morphism complex of the cylinder in the middle. And then we have another restriction map from the other pair of pans to the cylinder in the middle. And both of these are quotient maps. So, and then we identify the generators. We take all the generators in both pair of pans, and then we identify them in the middle. So I kind of drew this as categorically. It's like you get this part as a fiber product of. So the morphism complex for the whole thing is like a fiber product. So we'll come back to this page, but just want to say, so this Hamiltonian that we use to define this model of the Riemann category looks something like this. So again, this Hamiltonian is going to be linear near the infinity of each of the cylindrical ends, but for each bounded edge, it's going to look like this. So it's going to be positive quadratic. So this coordinate is a radial coordinates here, and we can have a Hamiltonian that just only depends on this radial coordinate, and then so it's going to be positive quadratic in this overlapping cylinder. Is going to be a negative quadratic and negative quadratic here. So what it does in the end is that this Hamiltonian will turn any Lagrangian negatively n times, and then positively 2n times, and then negatively n times. And then we assume like L alpha k is already had k alpha beta turns. So overall, there's n negative turns, 2n minus k turns, and then n turns. So that's what this Hamiltonian we want to use to define the Riemann category. So we are going to have a morphism complex that are Floer complex perturbed by by the Hn, and then the morphism complex for the Riemann category is going to be a direct limit as n goes to infinity. So let's see. So I actually, without even thinking about this Viterbo restriction, you can already start thinking about turning this very naively, because if you just try to, before we have this Hamiltonian, we can make the Hamiltonian satisfy the linearity condition in the ends, but then we can just pick the Hamiltonian to be identity in all the bounded part. If we do that, and then we compute all the holomorphic disks by brute force, then we'll see that there will be holomorphic disks that runs all over the Riemann surface, and we can't keep track of them. And then we can think about doing some turns in order to stop the holomorphic disks from going across the pair of pans just by some naive turns. But what's really going on is this kind of Viterbo restriction. Okay, so my explanation there was really vague, but I'll make it more concrete in a second. So, well, in this picture, I just want to, if you are curious about which points gets identified with which points, you can start labeling your points. So here we start with, so here in the middle, so this Hamiltonian has two stationary points. Like here, it doesn't get changed, so it gets negative turns, and then in the middle, every turn goes back to itself, and then it starts doing more positive turns, and then it goes back to itself after the negative turns again. So here, when it goes back to itself, we label it by x0, and then you can just keep labeling them. So these are the labels coming from this pair of pans, and then there will be labels coming from the other pair of pans, and then we identify them in this way, and that'll help us to match with whatever we get from the B side. So let's still come back and talk about this restriction map more. So what do we want to know for it to be like a restriction map? So we want our restriction map to be compatible with the A-infinity structures. So we can show a statement that if we have have a holomorphic disk with at least one input from this the complement of the cylinder. So if you only think about holomorphic disk in one of the pair of pans, and then if this holomorphic disk has one of the corner being like an input outside the cylinder, then we can show that the output is also in the cylinder. So it's like this action filtration thing from this as well. So, and then another statement we can show is that if you have inputs from more than one pair of pans in the white region, then as we keep increasing this n, this holomorphic disk will just get killed. So there won't be, for n large enough, given like a set of input points, then for n large enough, there won't be any holomorphic disk that goes all the way across. Okay, so I thought I'll just do some really messy sketch of why these are true. But it's going to be only going to be a sketch. So first of all, if we have the statement that if we have an input in here, then the output is in here, then essentially the complement of the cylinder part will be an ideal by itself. So that's how we have this restriction map as a quotient map. Okay, so and then it's compatible with the A infinity structure. So this restriction map will only have the first order. You can take the restriction and then take the A infinity products. So this restriction is a quotient map, and it only has a first order term. And to do that, well, the Viterbo restriction gives some conceptual ideas, but in this very simple case, it can be very concrete and elementary. So you can think about, what if my output is not in here but in there? So if my output is in the middle here, so I have this. I'm drawing. So this is a radial coordinate, and suppose my output is in this middle cylinder region, and then what I can get is I can either have a triangle that's entirely contained in the cylinder, or if I have inputs that's outside the cylinder, then there are only a couple of things that can happen. One is that we can have something like this, and then there's the output. I'll use this pen. And then, so the output will always have this big angle, just by the ordering of because well, this has to go counterclockwise, and then so this. Remember, we were computing polygons in this order, so we take the biggest perturbed by Hn of L1, and then we take something perturbed by H, and what? So we have to do something perturbed by n minus 1. So the thing is, we're going to. So if we count polygons, we'll end up having. So suppose these are the sides of the polygons. Then this curve is always going to have a smaller slope than this curve that goes the other way. And if so starting from these output points, we can have one curve that's the n perturbed one, and then the first perturbed one, so on. This is the nth perturbed edge of something, and then this is the n minus 1 perturbed edge of something. So this one is always going to have a bigger slope compared to the other one. And in all the cases that we had, this Lagrangians will never go out of this. It doesn't zigzag. It just goes through the cylinder once, and then once it goes out of the cylinder, it doesn't come back, and so on. So you just end up with this kind of schematic diagram with this kind of curve and then this kind of curve, and then once it goes out, it doesn't come back, well, without some other intersection points. So if you think of these two curves, and the Hamiltonian perturbation is kind of stationary right here, and then as we start turning on this action of the Hamiltonian, as we increase n, this one with a steeper slope is going to start intersecting this one. So as we increase n, this becomes just gone, gets killed. So there's now going to be a holomorphic disk with the input in this region, but with the output here. So if there's at least one input in this region, then the output has to be in this region. Okay, it's like the action filtration from there. When you take the differential, it always goes in this way to the bigger action. Yeah. So, but when we do this more concrete proof, we can see that this restriction map only has the order 1 term because it's compatible with the A infinity structures. Okay. And to show that there are no holomorphic disks that go through the entire, from this pair of pans to the other one, is kind of a similar idea. So suppose I have, so the inputs here, the inputs are going to kind of decide, it's like intuitively the inputs are kind of going to decide how much energy I have right here when I enter this cylinder, and then as I go through this middle, things start to cross. So as I increase, so for fixed inputs, as I start to increase n, I can show whatever holomorphic disk that I could have going across will get killed once I start turning on this Hamiltonian action. Okay, so well, you can break it into, there are some messy different cases where there's not going to be any inputs in the cylinder. If we can hope to have holomorphic disk going across, because any inputs will have degrees less than power 2, and the maximum principle will just make it just stop there. So you will end up with two curves, non-parallel, that goes through the cylinder, and then as the Hamiltonian action gets increased, they're going to start cross each other. Or if there's an output here, it's still the same behavior. So I think the main thing is to have this nice Hamiltonian that when we have Hamiltonian actions, the holomorphic disk gets killed off. So that was a little messy. Any questions about this construction of the restriction?
Is your Hamiltonian graph a fixed and finite number of times, like it's drawn on each cylindrical edge?
So this Hn is a globally defined Hamiltonian. So for each edge, I'll do n times. So for each Hn, I'll do n terms to n, and then I take the limit as n goes to infinity. So I need to make sure there are no holomorphic disks of certain type as n goes to infinity. So we have this restriction map. So we can have this morphism complex as the fiber product of each of the complex for the pair of pans. That's what this statement is saying. And then because there are no holomorphic disks that goes all the way across, the A infinity products of the Riemann category for the entire Riemann surface are given by those in the pair of pans. Because there's no ambiguity in this statement, because if the inputs are all in the cylinder, then we just get the output. It's just purely a computation in the cylinder. And if one of the inputs is in here, and then the output is in here. So we know which pair of pens we are doing this products in, and there's not going to be any product with inputs in both in two different pair of pens. So this is the computation for the rough category of this puncture Riemann surface. And actually, just from like the little, it was a little messy, but the schematic thing that we were saying that if you don't care about mirror symmetry, you just care about computing for category of surfaces or some other thing, like this technique can be, you can be a little bit more flexible, even if you don't have the puncture Riemann surface in this way. So suppose you just have any two things, and then they are connected by a cylinder. Maybe I'll draw how. So suppose you have any two parts that are connected by a cylinder, and you want to have a decomposition across the cylinder. So I haven't made this very precise, but just the ingredients that went into the proof of that. When can you use this technique in order to break things into two parts and glue them together? First, the thing that was needed was, so this cylinder is a circle, a bundle over this the middle part. So we need that the Lagrangian just go across. So you intersect each circle fiber just once. You shouldn't do something like, so this is a cylinder. So the Lagrangians, all the Lagrangians you want, if you don't have this hypersurface stuff, then you have to think about which Lagrangians are you picking to work with. So let's suppose we just take Lagrangians. We need in order to use this technique to break things, we need the Lagrangians to go all the way across, just intersecting each circle fiber once. And it wouldn't do something like zigzagging like this. Okay, so, yeah, it just doesn't, this technique doesn't really apply here. And also, it doesn't do any zigzagging in the cylinder, but it also, maybe I didn't, so I mentioned there was this part where I said once it lifts, it wouldn't come back without having another input point. So to do that, we have to require the Lagrangian, even once after it lifts the cylinder, even when it lifts the cylinder, so I have the Lagrangian going across, and even though it already left the cylinder, you still come back like in like a trivial way, and do something like and come back. So if you want to break things using this method, but however sometimes you want to come back. You could come back if you so we can choose Lagrangians that come back. So it goes all the way across the cylinder, and then it goes in here. But it can't come back like this, but it can come back after going through some other cylinder that breaks things. So if you want to have something that eventually comes back, we have to make it go through another cylinder so it doesn't influence anything when we come back. Okay. So I think I haven't made this really precise. This is a little bit just sketching, like thinking about how does this technique work if you want to study category for something, use this technique to do something slightly more general. If that's what you have in mind instead of just computing this for this puncture surfaces. Yeah, so that's that. And this is my last slide actually. So if you want to think about homological mirror symmetry, so we have some Riemann surface here, and then we can break it up into a pair of pens, and then we have this this restriction map here is a quotient map, just has the first order, like what we described before. And here we have, from the puncture sphere paper, we know there's a infinity equivalence. Well, even earlier work, just mirror symmetry for the pair of pans, A infinity equivalence to this C3 with the superpotential XYZ. I should write it down better. I just drew this thing. And then, sorry, this should be written down better. So it's C3 XYZ. And then there's just a very easy restriction. You just take, this is matrix factorizations. You just say let X be non-zero. And then that restrict to matrix factorization of this. And by this periodicity theorem is the same as the coherent sheaves on C star. So once I say X is now equal to 0, X becomes kind of the homogeneous coordinates. This X becomes like the homogeneous coordinates from this side. And then there's another set of coordinates. There's X prime that's non-zero that serves as, so X and S prime will serve as homogeneous coordinates kind of for the middle P1 here. So you have this restriction, and then we can show that these two functors are homotopic by computing some Homological cohomology that was done here. And then the rough category of the whole thing, and also is going to be the limit of these restrictions. And this matrix factorization for the whole thing is, you can compute it this way. It's also the limit, where you compute this as the same as the check model for computing a matrix factorization. And then the limit are also equivalent. So that proves homological mirror symmetry. So
the generation on the B side
the generation of the B side are generated by each
pair of tens.
Yeah, so there's so for each irreducible toric divisor is split generated by powers of an ample line bundle. And then you just take those. Yeah, so they're generated by the line bundles on each irreducible toric divisor. I copied from the puncture sphere paper. Oh, but this is really the classical result that the ample line bundle generates the.
But these are not compact. So.
Yeah, but the non-compact I think is easier. Yeah, like maybe I should think more, but yeah, because you can take all for all powers of k. So yeah, I think I kind of forgot. Yeah, if you want, you can even do like k for different orders on each edge. Well, I think the non-compact is if you can generate if you can compactify, you generate that, then you can. Well, then maybe I should think about it more. Yeah. So. Well, I guess I went too fast. So, any questions?
Questions. So, any questions?
Yeah. Yes.
So you chose this Hamiltonian to cut off the holomorphic disks
Right.
moving through the cylinder. Did you need so many generators in order to make that statement, or you chose a lot of generators for a different reason?
You mean the generating Lagrangian or just the generating
Lagrangians? You chose a lot of generators.
Oh, I chose a lot of generating Lagrangians. So I only need to choose L alpha 0 and but I chose it for OK in order to do this. It makes the mirror symmetry statement work easier. Like the mirror for each alpha K corresponds to this kind of line bound on the other side. But to just the generation for the K category, you just need 2 Lagrangians from each component.
So for the same Riemann surface, you can have several different Landau-Ginzburg mirrors. And
right.
I mean, well, for the same Riemann surface, you take different embedding to C star 2, and then you get different Landau-Ginzburg mirrors.
Right.
Yeah, so you think of
they're supposed to be, but because the Foucault category is supposed to be
certainly.
equivalent.
They should be the same. So is there a canonical isomorphism between various...
Well, you can go through this mirror symmetry. Yeah, but I don't think there is a trivial to see there. I mean, if you take 2 examples, you can play it and see that they are equivalent. But
if you choose the gluing not very well, perhaps even you get some non-toric Landau-Ginzburg mirror. Could that be the case? I mean, in order to patch up well into a global toric labial with a superpotential, I guess you choose the gluing well, but if you do not choose them well, you could get something different.
Yeah, if you choose the way that Minkowski did with this tropical limit, then there's this balancing condition that comes from tropical geometry, then you can do this. Otherwise, you have to, if you want to do mirror symmetry, you have to choose this decomposition well. But if you just want to compute the Foucault category, you don't have to.
I mean, the mirror can be non-toric, right? Just a non-toric variety with a superpotential. You could also do the case.
Yeah, that's a good question. I just think that, yeah.
Since time. There's a recent work of Niccolo Cibola and James Pascalet, where they also approach the Foucault category of a Riemann surface, also through restriction maps, but for different models of the Foucault category.
Yeah.
Do you have any sense if you have compatible restriction maps?
Yeah, I just met James briefly last week. Yeah, so I think he said they were doing this topological Foucault category, so it's a little bit different. But also they were kind of doing this in like a dual version. They have like so I have this restriction, so it's like a sheaf. I get this is like a sheaf model, but they're doing more like a co-sheaf. Yeah, because they're thinking more like this ribbon graph. That it's kind of a dual thing from this. Yeah. I don't have a better answer.
Is it possible to adapt some argument of yours to do some dual thing? I mean, is it possible to adapt some argument of yours in the case of non-wrapped Foucault categories?
Oh yeah, so that was what I was talking about. Like if you have compact ones, you don't need the wrap category, but you can think of like breaking them apart and somewhere in the middle by doing this.
Oh, I see.
But then it's kind of like wrapped, but
So I guess it's not so easy for conic vibration on the Riemann surface. Conic vibration on C star squared degenerating on the Riemann surface. Did you think about that case?
No, I just thought about the 2-dimension case. I should think about the higher dimension case too,
but yeah, you have some ideas on higher dimension.
Not a lot. Mostly Shio Ganatra had the Foucault. Yeah, I think he computed the Foucault for Foucault category of that.
So any further questions? So let's thanks the speaker again. For Thank you.